Hello everyone, welcome to the course on medical biomaterials. We will talk about some of the biomaterials used in cardiovascular and ocular area. We have been looking at quite a lot of biomaterial used in orthopedic as well as in dental. I thought another big area is cardiovascular and of course biomaterials used in eye. So, we will briefly touch upon the metals, the ceramics, the polymers used in this area. So, cardiovascular, they interact with the heart, blood and blood vessels. So, they have different functions. So, the failure modes could be mechanical failure, for example, if you have the left ventricle assist device or a diaphragm valve which opens, closes or a pump, heart pump, they can have mechanical failure. Thrombosis, blood clotting can happen because of the device, okay, and then blood vessels may get blocked. So, which can lead to strokes, paralysis, attacks, heart attacks. Hemolysis, because the material surface may be a little bit rough. So, it may activate your platelets, okay, the red blood corpuscles, they can start getting activated because of the friction, and then excess tissue growth surrounding this device. So, the tissues may start growing and which may lead to stress between the material and the tissue surrounding. Okay. So, these are divided into three categories: the temporary devices, that means like a tubing, simple tubings, oxygenators, arterial filters, hemodialysis, temporary internal devices. The previous one was temporary external devices, internal devices like your catheters, guide wires used for catheters, cannulae, and if any other angioplasty related activities done, there could be many temporary devices. Then permanent devices, vascular grafts, patches, pacemakers, defibrillators, stents, artificial hearts, all these valves and so on actually. So, we can have synthetic material, we can have natural or composite. Synthetic could be polymers, of course, metals. Natural could be biological and tissue engineered like pericardia, arteries, veins. Natural polymers like collagen, heparin. So, the biological tissues could be autogenic from the individual, allogenic from the same species or from a donor, xenogenic, it could be from animal. So, each has its advantages and disadvantages. So, titanium, stainless steel, nickel titanium combination, cobalt chrome, all these are used. Polymers, PTFE, PET, polyurethane, polyvinyl chloride, and biological could be pericardia, arteries, veins, heart valves, collagen, used as material for cardiovascular application. Metals of course are non-reactive, so good strength and biocompatibility, titanium, stainless steel, gold, silver, okay, they are used quite a lot in lead wires. Of course, disadvantages, there could be blood clotting. So, they have to be coated with some anticoagulant material, or the patients have to for lifelong take medication to prevent coagulation of the blood. That is a problem with metals actually. Okay. So, various cardiovascular implants, heart valves, silicone, PTFE, polyester, polyurethane, okay, or biologically derived material. So, all these are used. Okay. So, advantages, disadvantages. Okay. So, like some of these are very good. PTFE has good hemodynamic property, polyester is viscoelastic, polyurethane resistance to hydrolysis, but they could have calcification or thrombosis. Biologically derived material of course is very good, but then they are limited supplies. If you take metals, titanium, stainless steel, nitinol, all these are used in heart valves. Let us look at vascular grafts. PTFE, okay, is used, low thrombosis, high strength, of course disadvantages, immune response, PET, tissue ingrowth, biocompatibility is a problem. Biologically derived material, they are very good, but limited supply. Stents, a lot of metals are used, okay, originally titanium was used, stainless steel, nitinol, cobalt chromium, then again coated stents, drug eluting stents, they are very good, durable, low thrombogenicity, excellent hemodynamics. Composites, carbon fiber based epoxy, they are also very good strength. Pacemaker, leads, polyurethane, metals like titanium, stainless steel, cobalt, chromium, platinum, chromium and so on actually. Let us look at EPTFE, that is expanded polytetrafluoroethylene. Its longevity is very good. There is a manufacturer called Gore-Tex. This is a picture of this. Okay, this is used as a shunt. Okay, it is connecting different parts, especially aorta. Okay, this is used for cardiac reconstruction, vascular grafts, and pediatric shunts. These are all pediatric. So this is made up of PTFE. This may be about 2.5 mm diameter. Advantages: it encourages low thrombogenicity, lower rates of restenosis, hemostasis, less calcification, and biochemically inert. Okay, it is also resistant to allergic and inflammation. Disadvantage: negative immune response and thrombosis. PET, it is chemically inert, biocompatible. It is used in vascular grafts, large diameter vascular grafts. It is woven. You can coat it with protein or collagen, albumin, and so on to reduce blood loss. The crimped surface of PET helps stimulate tissue incorporation, promotes endothelialization on graft surface, no calcification. Of course, it can create foreign body reaction with greater possibility of thrombosis formation. Polyurethanes, it's thermoplastics, used quite a lot in medical applications, used in cardiac pacing leads, it is used in other areas also. High shear strength, elasticity, transparency, lacks flexibility and high chance of thrombosis. PE silicon copolymers are used in some of these to improve the flexibility. Okay. Silicon coating, pacing leads maintain electrical properties for better pacing than PU alone. Polyolefins, they have good biocompatibility and chemical resistance, especially polyethylene and polypropylene. Okay, so they are used as tubings, housings for blood supply, production of blood bags to store blood. Polypropylene is used for making heart valve structures, okay, and so on actually. Carbon and ceramics, carbon, glassy carbon, they are used in heart valve components. Pyrolytic, good biocompatibility and thromboresistance, high lubricity, resistance to wear. Graphite is used, pyrolytic carbon coatings, okay. Sapphire used as bearings in high RPM implanted rotary blood pumps. So, they have blood pumps for patients whose heart is very weak and the heart is not able to pump, then of course you have high RPM sapphires are used there as bearings. Ceramics, limited applications in cardiovascular devices. They are of course used in hermetic seals on pacemakers, insulation, and so on actually. Okay. Natural biomaterials, they are natural biological in origin, like autologous tissues, that is tissues from the same patient, you make use of it. So there is no immunogenicity problems, okay, rejection problems are there, but of course the supply is a big problem. Allogenic tissues, homografts, it is tissues from a donor, supply again limitations, there could be immune rejection. Xenogenic, this could be from animals, this is an alternate, but there could be transmission of disease. But there is a lot of interest nowadays in using animal tissues, especially for repair of valves, replacements, and so on. Of course, there also you can have immune rejection as well as disease getting transmitted. Okay. Bovine, porcine, equine tissues are generally used in cardiovascular applications. Okay. So, some of these blood compatibility of allograft, of course, the donor's own. So, very good, autografts best, strength and durability moderate, blood flow dynamics again is reasonably good. Okay. Submucosa of the small intestine, there is some interest in that, it is gaining popularity from porcine. It is prepared by opening the small intestine longitudinally, followed by mechanical removal of the submucosa layer while keeping the basement membrane intact. Okay, then you decellularize the extracellular membrane sheets and which you sterilize it actually. So, this submucosa of the small intestine, ECM, extracellular membrane, it contains collagen 1, 3, 4, 5, 7, fibronectin, elastin, and quite a lot of growth factors. So, they say it is extremely good, okay, for cardiac applications, for pericardial reconstruction. So, very good biodegradability, hemostatic capability, non-encapsulation, non-calcification. Of course, again The disadvantage is supply limitation, immunogenicity issue. Okay, so may be transmitting disease. Pericardium, a fibrous sac surrounding the mammalian heart. So you can harvest it from bovine or porcine, okay, and then it is decellularized and cross linked using glutaraldehyde for increasing the strength as well as preserving, and then this can be used for cardiac repair, reconstruction, valve repair, and pericardial closures. Mostly made up, this is mostly made up of collagen fibers. So easy handling characteristics, it's elastic, uniform suture retention, non-thrombogenic, resists infection. Big problem is calcification of pericardial grafts after implantation due to cross-linking with glutaraldehyde. Some anti-calcification techniques are also there, commercially available. If you look at bioprosthetic valves, these are for replacement of heart valves used in place of mechanical metal heart valves. This is again obtained from bovine or porcine. So it does not require anticoagulants. If you use metal, you may require that. Okay. Failure mainly due to calcification and tearing, lacks the strength, so it can tear or calcify. Injectable biomaterials like hydrogels made up of alginate, fibrin, chitosan. Okay. So they are very good, biocompatible, good chemical environment, able to deliver. It can improve cardiac function, reduce infarct size, increase wall thickness in the infarcted area. So if there is a wound or infraction, okay, it can cure it. Alginate hydrogels, they are used temporary ECM substitutes and as affinity binding moieties, enabling binding of proteins. So they can be used for controlled drug release. Fibrin glue as a sealant. Suppose there is a bleeding, and as you know, fibrin is a blood clot, so it can be used for preventing bleeding, speed up wound healing, and in drug and cell delivery. Chitosan hydrogels for delivery of proteins, drugs, and cells. Okay. Of course, engineered tissues, these are tissue engineered heart valves, still they are under research, okay, they are being explored, okay, but still they are not come into market. As a replacement for bioprosthetic or metal valves actually. Engineered, of course, they will be biocompatible, we can grow any type of cells on that, long duration and so on. Challenges are high mechanical strength to hold the blood pressure and contractive forces there. So basically you can make it using decellularized allo or xenografts, and cells are then seeded on top of that. Okay? That is the way in which it is made. As I said, it is clinically not been started. So what are the biomaterials for cardiac tissue? Scaffold based materials like collagen, elastin, fibrin, alginates, silk as scaffolds. Synthetic polymers like polyglycolide, PGA, polylactides, polycaprolactone. Collagen type 1 sponge scaffolds, okay, flexible and porous, allowing cellular integration. Alginate scaffolds, they help efficient seeding, retaining a high percentage of seeding cells and so on. Okay. Hydrogels, we looked at scaffold based materials, hydrogels, that means they use polymers which form hydrogels, natural hydrogels. We talked quite a lot about hydrogels, I will not spend much time, like gelatin, fibrin, alginate, agarose, hyaluronate. Synthetic polymer based, polyacrylic acid, polyvinyl alcohol and so on. So hydrogels is another approach, or decellularized tissues. Okay. So you take this tissues, allo or xeno, and then you decellularized, and then cells are seeded. Okay. ECM proteins and tissues have been evaluated as a potential scaffold to support various tissue. Homografts seeded with cardiac derived mesenchymal stromal cells. Okay. Fibrinal gel combined with human dermal fibroblast. Okay. So different types. So you need to do quite a lot of surface modification because the material has to be in contact with the blood. So you have to make it blood compatibility, whereas in other places we looked at bacterial biofilm issues, inflammatory issues and so on. So we need to here look at blood compatibility, hemolysis and so on actually. So different types of modification. We have spent a lot of time on surface modification, it could be physical, chemical or biofunctional type of modification. Physical could be simple coating a material like coating heparin. Heparin is used quite a lot as the anticoagulant, fibronectin, collagen, vitronectin and so on. Chemical means you couple a material or you graft the material, that is the chemical modification, like titanium nickel coating for ventricular assist devices and titanium oxide on metal stents, these are all chemical. Biofunctionalization, endothelium surrounds the entire vasculature, placing endothelial surface on the cardiovascular implants mimics the natural environment and thus allows better biocompatibility. So, several strategies are used for endothelial promoted surface modification by impregnating the surface with active molecules or vascular cell seeding, but of course, it is very expensive and time consuming. So, we can construct and immobilize early endothelial progenitor cells at the site of injury, which will secrete angiogenic cytokines which will flourish the resident, okay, and the late EPCs, ECs and EPCs. Okay. They are still under research and they have been tested quite a lot on animal models, but not on human volunteers. Another strategy is to construct the surface with the late EPCs, okay, endothelial progenitor cells, okay, which in turn promotes new angiogenesis and repair the damaged site by their native ability to proliferate. So, we looked at different types of materials that are used in cardiovascular, that is the heart, the valves, the diaphragms, the shunts, the stents, okay, and then of course, biologically derived material, trying to grow cells on top of okay, on top of some scaffold, injectable biomaterials, taking care of infarcts, taking care of wounds and so on actually. Next, look at some biomaterials that are used in the ocular, that means the eye. Okay. So, basically as you can see the retina is here, okay. You have the optical nerve which connects with the brain, this is the posterior chamber, this is the anterior chamber, we have the iris, the cornea here and the lens, this is the lens. So, there is a lot of biomaterials used in this place in the eye, okay. It is housed in a socket or orbit within the skull. So, we call this the orbit within the skull, and there is a soft tissue eyeball or a globe. Walls of the globe has 3 layers: outer scleral or corneal layer, intermediate vascular layer and inner retina layer. You can see this inner 1, 2, 3 here. Okay. Linkage of the globe to the central nervous system is achieved via this optical nerve. So, there are a lot of biomaterials trying to replace in this area. Okay. Ocular implants, orbital implants, that is orbit is this portion, right. So, that is orbital implant. So, if there are retinoblastoma, trauma, uveitis, rubeotic glaucoma, then you need to remove whatever is inside and place orbital implants. So, you remove the globe or its contents followed by implantation of devices into this scleral shell and conjunctival closure. So, glass, cork, ivory, aluminum. Okay. Then modern implants are hydroxyapatite or porous polyethylene. These materials help cellular invasion and vascularization, which in turn prevents biofilm formation and infection. So, these biomaterials are not meant to help the patient to see, but they are used just to fill up the orbit. So, originally some inorganic glass and ivory and aluminum were used, later on hydroxyapatite or polyethylene were used, so that there is a vascularization taking place, also it will prevent the biofilm formation and infection. Contact lenses, okay, this is mostly for correcting mild ametropia. So, you have hard, soft. Hard lenses are using polymethyl methacrylate. They have very good excellent optical properties, lightweight, satisfactory surface wettability. The main disadvantage is they got very low oxygen permeability. So, the patient cannot wear it for a very long time, the eyes become red. Okay. So, these rigid gas permeable contact lenses came into picture. So, it is a copolymerization of methyl methacrylate with methacrylate functionalized siloxanes such as methacryloxypropyl tris it is called. So, you copolymerized methyl methacrylate with the siloxane, trimethyl siloxysilane. So, when you do that, so we can change the cross linker ratio, so the oxygen permeability can be modified, elasticity, modulus of elasticity can be modified, hardness, wettability can be modified. Okay? That is called rigid gas permeable contact lenses. You also have these soft contact lenses. These are all hydrogels or silicon based material, polyhydroxy ethyl methacrylate hydrogels, okay, discovered in 1961. They have very good wettability, contains 38% water, comfortable to the wearer. Okay, so that is the soft contact lenses. So, other hydrophilic monomers used for the preparation of hydrogel lenses are N-vinyl pyrrolidone, glyceryl methacrylate. Of course, one disadvantage is the tear, they can get torn. The oxygen permeability, which is very important in contact lenses, it depends on the thickness of the lens and the amount of water that is present. So, oxygen permeability increase with water content. Okay. Second type of soft contact lenses are made up of silicone elastomer, polydimethyl siloxane PDMS. Okay, the first type is polyhema, second type is polydimethyl siloxane. It has excellent optical properties and also good tear resistance and high oxygen permeability. But the low surface energy leads to very poor tear wetting and hence a tendency to bind tear lipids and contact lens adhesion to the cornea. Okay. So, the low surface energy means it has got very high contact angle. So, when tear drops come down, it does not wet properly. So, the lipids get bound, okay, they get adhered to the cornea. So, there are many companies which make this contact lenses, as you can see from here list. I mean, you do not have to bother much, but basically look at this: silicone acrylate, fluorosilicone, fluoropolymer, silicone acrylate, hema, okay, pyrrolidone, okay, PDMS based material. So, a lot of material. So, and if you look at the water content, mostly the soft contact lenses you have very high water content. Look at the oxygen permeability, it is fantastic. When you have PDMS, water content is low, oxygen permeability is very high, because it become very hydrophobic, water content is very poor, but then oxygen permeability is very high. So, if you want to have a balance here, you know, some of these methyl methacrylate and vinyl pyrrolidone, water content is also high, oxygen permeability is also high. Okay. Intracorneal implants implanted within the cornea and therefore serve merely to augment the natural corneal function, to correct conditions such as myopia and hyperopia, made up of flint glass, then PMMA. PMMA, as I have been talking, good optical and mechanical properties, biocompatible, disadvantage, disruption of nutrient transport across the cornea, rejection, epithelial thinning over the implant, decreased keratocyte density anterior to the lens and stromal opacity. So, hydrogel intracorneal lenses now are being looked at, okay, to improve the nutrient transport, but then of course these have very poor refractive index when compared to PMMA type. Polysulfone intracorneal lenses have very high refractive index, but are impermeable to aqueous solution and hence prevents nutrient transportation. So, there is some problem if you are looking at hydrogels, or if you are looking at PMMA, or if you are looking at polysulfone based material. Okay. PMMA has very good optical properties, but the problem of nutrient transport. Hydrogels, okay, they have very poor refractive index, but nutrient transport is very good. Okay. Keratoprosthesis, what is this? This is a permanent indwelling device. This involves full thickness penetration of the cornea and result in the full substitution of the corneal function, that is penetrating total replacements of the cornea. Following the removal of epithelial layer and extraction of the underlying corneal stroma and endothelium, PMMA implant is placed in the extracted tissue, and this tissue with the keratoprosthesis are then sutured back into the eye, that is called a keratoprosthesis. This is carried out to improve the retention of keratoprosthesis. Collagen is coated on the implant, but PMMA keratoprostheses are still not largely used. Okay. These are now made from quite a lot of material like polyolefins and vitreous carbon and so on actually. Okay. Intraocular lenses, that is cataract extraction, after that they place a lens, intraocular lens it is called. These are very common nowadays, it is an ophthalmic surgical procedure. This is inserted to compensate for the loss of the natural crystalline lens. PMMA has been the standard for a very long time. Low surface energy results in both corneal endothelial damage or an insertion and post operative adhesion of inflammatory cells leading to iris adhesion, okay, to the IOL, that is intraocular. So, how do they overcome? They produce high polished surface, make both soft high energy surfaces using N-vinylpyridone and HEMA, hard low energy surface using perfluoropropane, binding of heparin and hyaluronic acid to the outer surface of the lens, coating with phosphoryl choline based polymer. So, different types of approaches are being used actually. So, reduce protein adsorption, cellular adhesion and neutrophil activation, reduce cellular deposition onto the lens. Okay. So, we looked at some of the biomaterials used in ocular region. Okay. As you can see, PMMA is used because of its very good optical properties, okay, but then it has got some disadvantages, okay, especially in oxygen transport and so on. And then we have soft contact lenses which will retain water quite a lot, like your HEMA. Then we also talked about nutrition, diffusion becomes a problem. Okay. So, you need to balance between all these various factors to achieve a good device to be placed in the eye region. Okay. Thank you very much for your time.